Hello everyone, my name is Nidhi Singh. I am assistant professor in Gyan Vihar School of Pharmacy. That is a part of the Suresh Gyan Vihar School. That is a part of the Suresh Gyan Vihar University. And today we are going to discuss this carboxylic acid, and it comes in your pharmaceutical organic chemistry first in your second semester. And we have already discussed some topics in the previous videos I've uploaded. So here we are going to study this carboxylic acid, the rest of the carboxylic acids, and let's start our topic. So the learning objective of this topic carboxylic acid is that here we are going to learn about the method of preparation of beta hydroxy acid, and also we are going to study about the physical properties of this hydroxy acid. These are the carboxylic acid derivatives, and also we are going to study about the preparation and chemical properties of hydroxy acids and the student outcome. They will be going to know about the preparation method of hydroxy acid. They will also learn about the properties of hydroxy acids, and they will also learn about what are the chemical properties and what are the preparation methods for the malic acid, tartaric acid, and the citric acid. These are the hydroxy acids, and these are the derivatives of this carboxylic acid because they are containing carboxylic acid in their structure. So firstly, the preparation of beta hydroxy acids. So like alpha hydroxy acid, similarly the beta hydroxy acid synthesized by using following methods. From first is your chlorohydrin, and here the chlorohydrin beta hydroxy. We have taken the beta hydroxy propanoic acid can be produced by the reaction of ethylene chlorohydrin with potassium cyanide followed by hydrolysis. So here the beta hydroxy propanoic acid, that is your beta hydroxy acid. So this beta hydroxy acid, this can be prepared by the reaction of this ethylene chlorohydride with the potassium cyanide, and then after the intermediate is formed, which is the hydrolysis, and there is a formation of this beta hydroxy acid. So here the chlorohydrin, from this chlorohydrin we are preparing this beta hydroxy acid. So in this you can see the reaction, and in the reaction there is the ethylene chlorohydrin, and there's the CH2CH2Cl OH plus KCl, that is your potassium cyanide, and then there is a formation of this intermediate, that is dinohydrin product is formed here, and after that this is a hydrolysis, and there is a formation of this beta hydroxypropanoic acid. So here there is a formation of this beta hydroxy acid from the chlorohydrin. So this is having chlorohydrin. This is having chlorohydrin. This is the chloro group is attached, and this is CH2CH2OH. So this is your chlorohydrin. So ethylene chlorohydrin, and this is your KCN, that is your potassium cyanide. When here this KCl is removed out and the CN will attach to this CH2CH2OH. Here a cyanohydrin product is formed, which is get hydrolysis, which is hydrolysis in the presence of this water, and there is a formation of this beta hydroxy acid is formed. Beta hydroxypropanoic acid is formed. Next is your by the action of nitrous acid. So here by the action of nitrous acid, beta hydroxypropanoic acid is prepared. This is the preparation of the beta hydroxy acid. This beta hydroxypropanoic acid is prepared by the different methods. So here the second method is your by the action of nitrous acid. So here we have taken the nitrous acid and we are treating it with the beta amino propanoic acid, and there is a formation of this beta hydroxy propanoic acid is formed here. So here you can see that on the beta position, this amino group is attached, and this is the propanoic acid. So that is why its name is beta amino propanoic acid. And when it is treated with this nitrous acid, and that is your HNO2, then HNO2, then there is a formation of this beta hydroxypropanoic acid. This is your beta because on the beta position there is a hydroxy group is attached. So there beta hydroxypropanoic acid is formed by the treatment with this nitrous acid. And this sodium nitrite is sodium nitrite in the presence of the sodium nitrite and the hydrochloric acid. So this beta amino propanoic acid is treated with nitrous acid, and in the presence of the sodium nitrite and hydrochloric acid form lactic acid. So this is the structure of your lactic acid that is uh, formed from your beta amino propanoic acid, that is also known as beta hydroxypropanoic acid. Lactic acid is also known as beta hydroxypropanoic acid. And you can see here that on the beta position there is a hydroxy group is attached, and COH group is also attached. That is a beta hydroxypropanoic acid or lactic acid. So by the treatment with this nitrous acid, there is a formation of this nitrogen gas is evolved on, and the water molecule is also formed here. So as you can see here, this amino group is removed out, and then from here OH group is attached, and there's a formation of this, and by this there's a evolution of this nitrogen gas. This NO2 gas is removed out, and the H2O is formed here. H2O is formed here. This is the formation of this lactic acid. Next is the third by the oxidation of 1,3-dihydroxy compound. So here the 1,3-dihydroxy compounds are oxidizes, and there is a formation of the beta hydroxypropanoic acid. So here beta hydroxypropanoic acid is obtained by the reaction of 1,3-propylene glycol with oxygen in presence of dilute nitric acid. So here you can see this is your 1,3-propylene glycol, and when it is oxidizes in the presence of your dilute nitric acid. So here we have taken the dilute nitric acid, and when this propylene glycol is oxidized, means here addition of oxygen. Oxidation means that there is the addition of oxygen. So here there is the addition of oxygen is occurring here, and there is a formation of this lactic acid or your beta hydroxypropanoic acid is formed here. So here you can see this 1,3-propylene glycol when it oxidizes in the presence of the dilute nitric acid. There is a formation of this lactic acid or your beta hydroxypropanoic acid. As you can see here, this CH2 is removed from here, and there is a attachment of this O. So there is a formation of this beta hydroxypropanoic acid is formed. Next is the physical properties of your hydroxy acid. So the physical properties of your hydroxy acids are physical state. So most of the hydroxy acids occur naturally and have several important biological properties. They are colorless, crystalline solids, or silky liquids. Hydroxy acids are more acidic than normal carboxylic acid. So the physical state means what is the appearance of that hydroxy acid. So in most of the hydroxy acids are occur naturally, like the lactic acid. Lactic acid is present in the milk, soy milk. So they are occurring naturally, and they are having some important biological properties. They are also having biological properties, and they are colorless. They are colorless, crystalline. So they are having no color. They are having crystalline solid. They are in crystal form or silky liquids. In silky liquids, and in the syrup form they are in liquids. And the hydroxy acids, these hydroxy acids are more acidic than your normal carboxylic acid. So these hydroxy acids are more acidic than your normal carboxylic acid, because they are having the OH as well as your COOH2. They are more acidic than the normal carboxylic acid. So this is the physical state that most of the hydroxy acid they occur naturally and have several important biological properties. They are colorless, crystalline solids or silky liquids, and their hydroxy acids. These hydroxy acids are more acidic than the normal carboxylic acid. Next is your solubility. So the solubility of this, the hydroxyl derivatives are often containing OH and COOH group, which form hydrogen bond with water. Therefore, they are more soluble in water than the corresponding carboxylic acids. So these solubility is that the hydroxyl derivatives, because the hydroxyl derivatives, as you can see, as you have seen in the structure, that they are having the both OH as well as the COOH group in their structure. So they can form a hydrogen bonding. So they can form a hydrogen bonding with the water. That is why they are more soluble in water as compared to the carboxylic acid. Uh, Next is your boiling point. So the boiling or melting point of hydroxyl acid are all higher than the corresponding carboxylic acid. So the boiling and the melting point, the boiling or melting point of carboxylic acid, these are having higher this carboxylic and the melting, this boiling and the melting point of this hydroxyl acid. These are higher as compared to the corresponding carboxylic acid. So, physical properties of your hydroxy acid. First was the physical state, second solubility, and the third is the boiling point. So, in the first physical state, that the most of the hydroxy acids are occurring naturally, and they are having some important biological properties, and they are colorless. They are colorless. They are crystalline solids. They are having crystalline solids. They are syrupy liquids, and these hydroxy acids are more acidic. These are more acidic than normal carboxylic acid. And the solubility is that the hydroxyl derivatives, these hydroxyl derivatives, they are containing both OH as well as the COOH group. So that is why they are forming hydrogen bonding with the water, and they are more soluble with water in water as compared to your carboxylic acid. And third is your boiling point. So the boiling point of this boiling as well as their melting points are higher compared to the carboxylic acid. So these are the physical properties of the hydroxy acid. Now the preparation and chemical properties of this hydroxy acid. Now what are the preparations and the chemical properties of this hydroxy acid? So the method of preparation, physical and chemical properties of some of the individual hydroxy acids along with their uses have been described here. So here the method of preparation as well as their physical and the chemical properties of this hydroxyl acids are given, as well as their uses are also we are discussing today. So first of all, the first hydroxy acid is the malic acid. So in this you can see there are two functional groups attached on this malic acid, which that is a hydroxy, and then the COOH. That is why they are the hydroxy acid. OH for your hydroxy and the COOH for your acid. So the both of them are attached. That is why they are known as the hydroxy acid. So this malic acid is a hydroxy acid. The malic acid is an organic compound with the molecular formula C4H6O5. It is also known as hydroxyl butane dioic acid, which is dicarboxylic acid that is made by all living organisms contributes to the pleasantly sour taste of fruit and is also used as a food additive. And malic acid is a colorless crystalline solid soluble in water and alcohol but sparingly soluble in ether. It melts at 130 degrees centigrade, and the malic acid contains one asymmetric carbon, hence it exists in two optically active two isomeric form uh, two isomeric and stereoisomeric form LND isomers and one inactive form to only the L isomer exists naturally. So here this malic acid, the structure of this malic acid is given here. That is your OH, COOH, CH2, COH. So in this The malic acid, this malic acid, this is one of the organic compound which is having the molecular formula that is a C4H6O5, and it is also this malic acid is also known as your hydroxyl butane dioic acid. So this malic acid is also known as your hydroxyl butane dioic acid, that is your OH, and you can see here its name is given like this: 1, 2, 3, 4. So this is your 1, 2, 3, 4. So 1, 2, 3, 4. This it is containing four carbon atoms. That is why it is butane and dioic, because here the two carboxyl groups are present. So its name is butane dioic acid, and OH because of hydroxyl group is present. So this hydroxyl butane dioic acid, we can also call it like this: hydroxyl butene dioic acid, and second name is your malic acid. So it is a dicarboxylic acid. You can hear that it is having the two carboxylic acid that are present in this structure. So it is a dicarboxylic acid that is made by all living organisms. It is made by all living organisms, contributes to the pleasantly sour taste of fruits. Means here it is contributed to the pleasantly sour taste of fruit. Means due to its presence, there is a sour taste in the fruits, and it is also used as this malic acid is also used as a food additive, and the malic acid is a colorless crystalline solid which is soluble in water and alcohol. So this is a colorless crystalline solid. As I have told you, the physical property of this, that physical state, that these hydroxy acids appear as a colorless as crystalline solid. So this malic acid is also a hydroxy acid. That is why it is also a colorless crystalline solid, and this is soluble in water and alcohol, but sparingly soluble in ether. But they are little much soluble in the ether, but they are fully soluble in the water as well as in the alcohol. And it's melting. It melts at 130 degrees centigrade. So these malic acids having a high melting point. That is why it is having 150 degree centigrade melting point. So here, melting acid, malic acid, contain one symmetric carbon. Asymmetric carbon, hence it exists in two optical active, active and one inactive form, and two only allyl isomer exist naturally. So here you can see the malic acid is containing one asymmetric carbon. So the asymmetric carbon is your this. This is your asymmetric carbon because it's the four sides are bonded to the different atoms. So here you can see this is the COOH function group. It is bonded to this, and here one side is your OH and one side is the H, and one side is the whole. This whole is attached to this. This whole carbon is attached to it. That is why this carbon is your asymmetric carbon, and it is existing in two forms, two optically active forms. That is your stereoisomeric form. That is L and the D. As you can see, the D, this is the D form, and this is the L form. As you can see, the OH is present on the right side. That is why it is the D form, and this is the L, D dextro, and L is a levo, and here OH is present on the left side, so it is your LIBO form. And one inactive form, as you can see, this carbon is an inactive form because this carbon, this carbon here, both side hydrogen is attached, and one side is COOH is attached. But the both sides is H attached, that is why it is an inactive form. And only L isomer exists naturally. So only this L malic acid exists naturally. So this malic acid, this is an organic compound that is having a molecular formula C4H6O5. So C4 because four carbon atoms are there. H6, this 2, 3, 4, 5, 6. So H is your 6 and 5, 2, 2, 4, and 5 oxygen. So this is the molecular formula of the malic acid C4H6O5. and it is also known as hydroxybutene acid, and it is also known as hydroxybutane dioic acid. So it is a carboxylic. Um, it is a It is a dicarboxylic acid that is made by all living organisms, contributes to the pleasantly sour taste of few fruits, and it is also used as a food additive. And malic acid is a colorless crystalline solid that is soluble in water and alcohol, but sparingly soluble in ether. It melts at 130 degrees centigrade, and the malic acid contains one asymmetric carbon. Hence, it exists in two optically active, that is, a two stereoisomers form, that is, a levo and the dextroisomers, and one inactive form, though only the L isomer exists naturally. So these are the two forms of this malic acid, in which the one asymmetric carbon is showing the two forms, the optically inactive, that is a D optically active, that is a dextro, and the levo. Next is the preparation of malic acid. So the malic acids can be prepared by the following methods. So by the action of nitrous acid and alpha aminosuccinic acid, that is aspartic acid. So malic acid can be obtained by the reaction of nitrous acid on aspartic acid. So this CHNH2COOH, CH2COOH, this is aspartic acid, or you can say the alpha aminosuccinic acid. Means on the alpha carbon, this amino acid is attached. So it is your alpha aminosuccinic acid, or you can say aspartic acid. So it is treated with this nitrous acid, and when this is treated with this nitrous acid, there is a formation of this malic acid plus nitrogen gas plus water molecule. So this malic acid can be obtained by the reaction of nitrous acid on aspartic acid. Second reaction is now by the partial reduction of tartaric acid. Malic acid can be prepared by the reduction of tartaric acid with this hydrogen iodide. So this is your tartaric acid, and this tartaric acid is reducing with this in the presence of this hydrogen iodide. There is a formation of this. There is a formation of this malic acid is formed here, plus iodine plus water molecule is removed out from here. So the first method for the preparation of your malic acid is by the action of nitrous acid on alpha aminosuccinic acid. So here malic acid can be obtained by the reaction of nitrous acid on aspartic acid. So here you can see this from here this amino group is removed out, and from here OH is attached to this carbon atom, and here nitrogen, because two nitrogen are present, that is why nitrogen gas is brought out, and this HO2 it formed with this. Here the water molecule is removed out from here. So there is a formation of this malic acid is formed. Secondly, by the partial reduction of tartaric acid, means it is partially reducing of this tartaric acid is occurring. So this malic acid can be prepared. It can be prepared by the reduction of tartaric acid with hydrogen iodide, and you can see that tartaric acid is reacting with this sodium hydrogen iodide, and there is a formation of this malic acid is formed here. So what is happening here? It is happening that this OH is removed out from here, and here from here H is being added to this CH. So there is a formation of this CH2COOH, and here from here this H2O. This is because here two molecules of this hydrogen is there, so two H2O are formed here, and here I2 means iodine is also evolved out from here. Third method is your from bromosuccinic acid. So this is the structure of your bromosuccinic acid, and when bromosuccinic acid is treated with moist silver oxide, so there is a formation of this malic acid is obtained. So bromosuccinic acid is reacted with this silver oxide, silver hydroxide, and there is a formation of this malic acid plus AgBr. So from there, the Br is removed out, and this OH is being replaced. This OH is being replaced to this Br, and there is a formation of this malic acid, and this Br, which is removed out from there, that gets added or that bonded to this silver. There is a formation of silver bromide. So they so there are this is a method for the preparation of malic acid. The first method was the action of nitrous acid on alpha aminosuccinic acid. Second is your by the partial reduction of tartaric acid, and the third is your from bromosuccinic acid. And next is your chemical properties of your malic acid. So malic acid possesses following chemical properties. First is your action of heat. So by the action of heat, there is a formation. This malic acid gives a different product. So this malic acid is giving the malic anhydride. So as you can see that malic acid undergoes dehydration and heating to form malic anhydride. Means there is a removal of this water molecule from this malic acid. So here, first in the first reaction, you can see that malic acid is dehydrated on heating, and there is a formation of this fumaric acid. So this fumaric acid is formed here. So this fumaric acid is formed here. So here you can see this OH, this OH, this OH and this H. This OH and this H has been removed out from here, means here the water molecule is removed out, and there is a formation of this double bond is formed here. You see the double bond is formed here. So this is your fumaric acid. Now fumaric acid is again heated, and there is a formation of this malic acid. This is a malic acid and this is a malic acid formation. The difference is that there is a double bond between this carbon-carbon, and in this is a OH and H is attached to it. So here you can see this is your malic acid. So here this is the isomeric form. Means there is a conversion of this hydrogen to this place. So this is your malic acid. Next is your this malic acid. Again from here the water molecule is removed down, and there is a formation of this malic anhydride is formed. This malic anhydride is formed here from the malic acid. So the malic acid is heated, and there is a removal of this water molecule. After that, there is a formation of this fumaric acid, and fumaric acid is again heated, and there is a formation of this malic acid is formed there. So this malic acid is again heated, and there is a formation of this malic anhydride is formed. So there, this malic anhydride is formed from this malic acid. Next is the oxidation with KMnO4. As you know that KMnO4 is the oxidizing agent. So the oxidation will occur with this KMnO4. And when we are treating this malic acid with this KMnO4, there is oxidation occurring here. So there is a formation of an oxaloacetic acid is formed. So from here, the oxaloacetic acid is formed here. So water molecule is removed out, and there is addition of the oxygen on the carbon atom. As you can see, the oxaloacetic acid means here this is the keto form. So this is the keto group attached to it. This is the keto. So from here, this H and this OH is removed out, and here the oxygen is added. So there is a oxidation occurring from this malic acid to this oxaloacetic acid, and there is a formation of this keto form. And this keto form, this is the keto form, and this is the enol form. So here the tautomerism is occurring. This is the isomerism. This keto form to enol form, keto enol tautomerism. This is the tautomerism that is occurring. That is a type of isomerism. So here you can see this is the keto form, and then here OH is attached, and there is a double bond between this, and this is the enol form. So enol means in double bond is here, and the OH group is here. So it is your enol form, and this is your keto form. Keto, and there is a CO group is attached, and when there is a OH is attached, then it is a enol form. So this is the keto enol form. So this is the malic acid, and this is the malic acid, and malic acid on oxidation gives their oxaloacetic acid, which exists in ketoenol tautomeracy. So here, this in this the KMNO4, that is a potassium permanganate, which is um, oxidizes, which is acting as an oxidizing agent. So it is oxidizing this malic acid to the oxaloacetic acid, and this oxaloacetic acid is mm, existing in a ketoenol tautomeracy. So this uh, malic acid, when it is oxidizing with this KMNO4, there is a formation of this oxaloacetic acid, and this oxaloacetic acid, this is a keto form which is existing in a ketoenol tautomeracy. So there are two forms, that is a keto form and the enol form. Next, this is the this chromic acid is also an oxidizing agent. So this is also oxidizing the malic acid. So this chromic acid, on oxidation with the chromic acid, this malic acid is converted with the malonic acid. So this is converting it into the malonic acid. So but in the when there is a KMNO4, means potassium permanganate is there. So there is a conversion of malic acid to the oxaloacetic form. But in case of this chromic acid, which is also a oxidizing agent, so this is oxidizing the malic acid to your malonic acid. So this malic acid, this malic acid is oxidizes with the chromic acid, and there is a formation of this malonic acid, and there is a from malonic acid is converted to the malonic acid. So here you can see there is a formation, this CH2 is bonded to this COOH, and from here there is a removal of this COOH, means there is a removal of this COO2, means here carbon dioxide is evolved out plus water molecule is evolved out. There is a formation of this malonic acid. So an oxidation with chromic acid, malonic acid converts into malonic acids. There is a formation of this malic acid oxidizes by this chromium acid, and there is a formation of this malonic acid, and plus carbon dioxide is evolved out plus water molecules formed. Next is the reduction. So this is the fourth reaction of this chemical properties of this malic acid. So in this, the malic acid reduces with hydrogen iodide, and there is a formation of this succinic acid. So this succinic acid is formed here. So malic acid, when it reduces with this hydrogen iodide, there is a formation of this succinic acid is formed here. So in the reduction, malic acid is reduced with hydrogen iodide, and there is a formation of this succinic acid is formed here, plus H2O plus iodine is formed here. So malic acid plus hydrogen iodide, there is a formation of this succinic acid. So this OH is removed out from here, and there is an addition of this hydrogen. Means the reduction means the addition of hydrogen. So here the H is added to this position, means this position CH, and there is a removal of this OH is removed out from here. The succinic acid is formed here, and plus H2O, water molecule is formed here, plus iodine is formed here. Next is your malic acid. So malic acid is used in the preparation of several esters and salt. So malic acid is used in the preparation of several esters and salt. And secondly, as a substitute of citric acid in drinks, and in the preparation of medicine of sore throat. So here, this malic acid is used as a substitute of your citric acid in drinks, and it is also used in the preparation of your medicine of sore throat, and it is also used in the preparation of several esters and your salts. Next is your tartaric acid. So this is the structure of your tartaric acid, and tartaric acid Tartaric acid is also a carboxylic acid, because it is also containing this carboxylic acid, and it is found in many plants, and particularly tamarind and the grapes. So the tartaric acid is present in tamarind and the grapes. and it is a dicarboxylic acid. And the tartaric acid is also known as alpha dash dihydroxy succinic acid. Why? Because this CHCOOH is the structure of the succinic acid, and CH2COOH. So this is the structure of succinic acid, and on the alpha position of both the carboxylic acid in respective to this carboxylic acid, the hydroxy group is attached, and that is why it is also known as alpha dash dihydroxy succinic acid, and the IUPAC name is your 2,3 dihydroxy butane dioic acid, because four carbon atoms are there, that is why butane, and dioic because the two carboxylic acids are present, so this is dioic acid. And on the second and the third position, the two hydroxy groups are present, that is why 2,3 dihydroxy butane dioic acid. And it is a colorless crystalline solid that is soluble in water and alcohol. So it is also, as I have already told you, that the hydroxy acids are colorless crystalline solid. So it is also a colorless crystalline solid, and that is soluble in water and alcohol. But malic acid soluble in water and alcohol, but it is but it is sparingly soluble in ester. But in this case, it is colorless crystalline solid that is soluble in water and alcohol, and it melts at 170 degrees. So this tartaric acid is melting at 170 degrees, and the malic acid melts at 130 degrees. So it has an acidic taste. It has an acidic taste, and this tartaric acid has two identical asymmetric carbon atom, and these exist in four stereoisomers form: dextro, meso, meso, and racemic form. Because both the carbon are having in the four different bonded to the four different groups, or you can say the atoms also. So here the tartaric acid is a dicarboxylic acid that is found in many plants, that is tamarind and grapes, and it is also known as alpha dihydroxysuccinic acid, and it is a white crystalline solid, colorless crystalline solid, and it is soluble in water and alcohol, and it melts at 170 degrees. And it has an acidic taste, and this tartaric acid has two identical asymmetric carbon atoms that exist in four stereoisomer form, that is a dextro, meso, meso, and racemic. So this in this B tartaric acid, tartaric acid, mesotartaric acid. So as you can see here, that D in this, you can see here, this carbon is attached to the four different atoms in the group, and this carbon is also attached to four different atoms of group. In this LIGO, there is this tartaric is also attached, but here this you can see this OH is on the left side, right side. So this is the D form, and this also hydroxy is on the right side, left side. So this is the LIGO form. So this is a mesotartaric form because here both are having the same. Okay, this is also having the same, and this is also, and this is a racemic form. As you can divide it in a plane of polarized plane, then this is also having the same, this is also having the same. So dextrorotatory tartaric acid is found naturally in grapes, berries, plums, and several other fruits, and levotartaric acid is obtained chiefly by resolution of racemic tartaric acid. So the racemic tartaric acid, that is an equal mixture of D and L. So this D and L, this is a mesotartaric acid, this is the equal form of this D and N, is prepared commercially by the molybdenum or tungsten catalyzed oxidation of malic anhydride with hydrogen peroxide. So the preparation of tartaric acid. So the tartaric acid can be prepared by the following general method from glyoxal. So on treatment with hydrogen cyanide, glyoxal produces glyoxal cyanohydride, which on hydrolysis gives tartaric acid. So you can see this is a glycosol, and when it is treating with this hydrogen cyanide, there is a formation of this glycosol cyanohydride, and on this, which on hydrolysis it is giving this tartaric acid. Second is your Kilani-Fischer synthesis. So in the Kilani-Fischer synthesis, it is one of the methods in which there is an increased number of carbon in compounds, and the tartaric acid can also be formed from glyceraldehyde. So this is a glyceraldehyde. When it is a hydrogen, when it is treated with this hydrogen cyanide, then there is a formation of this intermediate, and when it is hydrolyzed, there is a formation of this intermediate, and this when it is treated with this nitric acid in and oxidizes, there is a formation of this tartaric acid. Next is your from alpha-alpha dibromosuccinic acid. So in this, both alpha and negative means dextro and the LiPo and mesotartaric acids are prepared by boiling alpha-alpha dash dibromosuccinic acid with moist silver oxide. So here you can see this is your alpha-alpha dibromosuccinic acid structure, and then it is treated with this silver oxide. There is a moist silver oxide, then there is a formation of this tartaric acid plus this silver bromide is formed here. So by the oxidation of fumaric acid. So this is the structure of your fumaric acid, and when this fumaric acid is hydrolyzed, or you can say the oxidizes in the presence of this KMNO4, that is your potassium permanganate, there is a formation of this tartaric acid is formed. Next is your chemical properties of your tartaric acid. So the chemical properties of tartaric acid are as follows. Firstly, it is the oxidation. So with mild oxidizing agent, tartaric acid is tartaric acid, while with strong oxidizing agent, tartaric acid forms oxalic acid. So this tartaric acid, when it oxidizes, it forms tartaric acid, and when it is treated with a strong oxidizing agent, then it is formed oxalic acid. However, on oxidation with Phantom reagent, in Phantom reagent is alkaline H2O2 plus FeSO4, the tartaric acid is oxidizes into dihydroxy malic acid. So this tartaric acid is when reacted with this Phantom reagent, then there is a formation of this dihydroxy malic acid is formed. Next is the reduction. So in the reduction, tartaric acid, when it reduces with in the presence of this hydrogen iodide, then there's a formation of this malic acid. After that, again, when it is reduces, then there's a formation of this succinic acid. So here you can see in the reaction, tartaric acid is reduces with this hydrogen iodide, and there's a formation of this malic acid. After that, it is again reduces, and there's a formation of this succinic acid. So with HBr, the tartaric acid is reduces to bromosuccinic acid. So here the tartaric acid is reduced to bromosuccinic acid with the treatment with your hydrogen bromide. And there's also a formation of, or you can say the removal of your water molecule. Next, your action of heat. So when tartaric acid is heated at 150 degrees centigrade, it decomposes into tartaric anhydride. So this tartaric acid, when it is heated and there is a removal of water molecule, there is a formation of this tartaric anhydride is formed. So tartaric acid, when is heated, it decomposes into tartaric anhydride. And on strong heating, it decomposes into pyruvic acid with the evaluation of CO2. So this tartaric acid is heated with this tartaric acid. When it is heated on strong heating, it is decomposing into your pyruvic acid, and also there is a evolution of your carbon dioxide plus water molecule is evolved out from there. Next is the tartaric acid. So the uses of this tartaric acid is used as in the preparation of your baking powder and effervescent beverages, and in mirror silvering in the form of sodium potassium tartrate, as mordant in dyeing and calcium printing. So these are the uses of this tartaric acid. Next is the citric acid. So this is the structure of the citric acid. So citric acid is a weak organic tribasic acid having the chemical formula. It is having C6H8O7. So here you can see this is having C6, means carbon is here 6 and oxygen is 7 and hydrogen is 8. So 2 to 4, 5, 6, 7, 8. And oxygen 2, 4, 5, 6, 7. 7 oxygens are there. So the IUPAC name of citric acid is 2-hydroxy propane 1,2,3 tricarboxylic acid. So the IUPAC name of this citric acid is 2-hydroxy. On the second position of the carbon atom, there is a hydroxy group is attached, and this is a propane, and on the 1, 2, 3 position, the tricarboxylic acid is present. It occurs naturally in citric acid fruits like lemon, oranges, tomato, etc. And citric acid is also a crystalline solid that is containing one water molecule, and it is soluble in water and alcohol but sparingly soluble in ether. And at 130 degree, it loses water molecule in the anhydrous acid melt at 150 degrees centigrade. The first reaction is your Bloombox atom synthesis. In this, firstly, the 1,2,3 hydroxypropane will converted into your 1,3-dichloro-2 propanol. Then it is converted, oxidizes to form the 1,3-dichloro-2 propanol. Then it is again, there is a formation with the cyanohydrine. There is a formation of 1,3-dichloro-2 cyano-2 hydroxypropane. After that, with the acidic hydrolysis, there is the formation of this alpha chloromethyl alpha hydroxypropanoic acid. After that, there is a reaction with this potassium cyanide. There is a formation of this beta cyano alpha cyanomethyl alpha hydroxypropanoic acid, which is again acidification. There is a formation of this 2-hydroxy 1,2,3 tricarboxylic acid, that is a citric acid. By Haller-Helg synthesis. This synthesis occurred in 1890s. So in this synthesis, firstly, the ethyl beta keto butyrate is reacted with this chlorine, and there is a formation of this ethyl gamma chloro beta keto butyrate, and again it is reacted with this KCN, and there is a formation of this ethyl gamma cyano beta keto butyrate, and again this KOH with the reaction of KOH, this is formation of the keto butyric acid, and when it is reacted with this KCN, and there is a formation of this acid is formed. By the Dunksman and Pacman synthesis. In this synthesis, ethyl gamma chloro beta keto butyrate reacted with the KCl, and there is a formation of this ethyl beta keto butyrate. And when it is reacted with this HCN, there is a formation of this ethyl beta cyano beta hydroxybutyrate. After that, with the treatment of HCl and water, there is a formation of this oxalic acid is formed. By reform-Maxey reaction, so citric acid is obtained by the reaction of ethyl bromoacetate with the oxaloacetate plus zinc. So there is a formation of the citric acid by the hydrolysis. Then the chemical reaction. So the first chemical reaction is the citric acid from 3 types of salts. That is citric acid is tricarboxylic acid. Therefore, it forms a 3 series of salt, that is a monophosphate citrate, diphosphate citrate, and the triphosphate citrate. Now the action of heat. On heating with 150 degrees centigrade, the acetic acid undergo dehydration, and there is a formation of aquanitic acid. And by heating with fuming sulfuric acid at 150 degrees centigrade, the citric acid gives acetone dicarboxylic acid. And the reaction with acetic anhydride. So this citric acid is reacted with acetic anhydride, and there is a formation of this monoacetyl citric acid, and on the reduction in presence of this hydrogen iodide, citric acid reduces to tricarbolic acid. So there is a formation of this tricarbolic acid from the citric acid. And the uses of this as flavor compound in preparation of synthetic fruit drinks, as laxative in the form of magnesium citrate, as solvent in polymer synthesis, as an iron supplement in the form of ferric ammonium citrate, as modern in printing and dyeing. So these are the questions. Citric acid is a tribasic acid. Which of the following is most common method for citric acid production? That is the submerged filtrate fermentation. Next is citrate. Citrate is a feedback inhibitor of phosphofructokinase, and the magnesium hydroxide is used to precipitate potassium citrate. That is false. When propanoic acid is treated with sodium and bicarbonate, carbon dioxide is separated, and the C of CO2 comes from bicarbonate group. And the benzoyl chloride is prepared from benzoic acid by SOCl2. Citric acid cycle occurs in mitochondria. Next, acetamide is treated separately with the following 6 reagents. Which one of these would give methylamine? So this is your NaOH plus Br2. So these are the references from where you can study this topic. And thank you so much for today's lecture.